So we've talked a little bit about finding matrices for linear transformations from Rn to Rm and being able to show that you can do them through matrix multiplication. Well, the point of this particular lecture, and what we're going to talk about in this section, is the idea that we can do this for any transformation, or at least any transformation that we are going to deal with. So, to that end, let's let T be a linear transformation from V to W. V and W are both finite dimensional vector spaces. That just means that they have a basis that's a finite set of vectors. So, we'll denote the basis for V by B, and denote the basis for W by B prime. All right. Certainly, if we know how the certainly since we know that B is a basis, I can write X as a linear combination of the basis vectors. And since T is a linear transformation, I can write the image of X in terms of the vectors in B. So just to do that, suppose we have X as our linear combination. I apply the transformation to X. I use the properties of the linear transformation to pop the break it up over the sums, and then pop the constants out. So, what this means is that as long as we know the images of the basis vectors, as long as we know what the image is for everything in B, we can compute the image for every single vector. So, once we know what the transformation does to the basis vectors, we know exactly what the transformation does. All right, now let's concentrate on those basis vectors. Certainly each v sub I is the image of each v sub I. So if I apply t to each v sub I, it's a vector in W. It's a vector in W, sorry. That means that we can write the image as a linear combination as the vectors that are in B prime. So, in other words, for V1, I can write that as a linear combination of the W1 out to Wm. And I'll denote those constants that we're using as A11, A21, and so on. Do the same thing for the image of V2. So then we have A12, A22, and so on down the line until we get to the image of Vn. All right, so now, let me go back real quick. Now notice that I've written these subscripts that kind of look backwards for how we would have written them in the matrix. But we have done the following. We've certainly taken constants and written them as columns in a matrix. This is exactly what we're going to do here. So that A11, the A21 onto the AM1 were the coefficients on the W's to give us V1. The A12, the A22 down to the AM2, those were the coefficients on the W's to give us the V2, and so on. Certainly, when we're talking about coordinate vectors, the coordinate vector of V1 relative to B is just, well, we need one copy of V1 and 0 of the rest of them. So now let's look. If I take the matrix A and multiply it by this coordinate vector, notice all I get is the first column of A. But those are exactly the coefficients that gave us the linear combination of the W's. Those are the coefficients on the W's. That's the linear combination of the W's that gave us the image of V1. So when we take those numbers and write them as a coordinate vector, that A11, A21, and so on, that's the coordinate vector of the output with respect to B prime. And in general, we get the exact same thing for any of the other basis vectors. So if your basis vector VI has this particular coordinate vector, and certainly it does, because the coordinate vector of VI will just be one copy of VI, so this is in the I spot, and zeros everywhere else. If you take the matrix A, concentrating again on column I, and multiplying it by that coordinate vector, when we multiply it, the only thing that comes out is column I. All right, so hence, and this is off of the screen again. Let's see if I can pause this and get it back on the screen. Here, I wanted to get that on the screen for you so you could see it. Hence, the image of the V sub I, the coordinate vector of that relative to the B prime, is just that ith column, which is exactly the coefficients in that linear combination that we use to get to the image of VI. All right. So to recap, the way we formed that matrix A was first we computed the image of the basis vectors in B. Okay, this is the basis vectors from V. We found the coordinates of those images was with respect to B prime, and then put those coordinate vectors in as columns for A. Now let's show how we can use this A to compute any image that we want. So let's say our coordinate vector of V is that C1 out to Cn. Then certainly I can write C1 out to Cn as a linear combination of the 1, 0, 0, 0, 1, 0, and so on down the line, so that when I write that linear combination, I can pull a breakout that can distribute the A over the sum and then pop the constants out in front. But A times this are those images of the basis vectors. And now I can see what the coordinates of X are, the image of X are, relative to B prime. Well, the first coordinate is just take the C1 times the A11, the C2 times the A12, the Cn times the A1n, and add them all together. Likewise, you do the same thing for the second, the third, and so on. So the last component, the mth component, will be C1 times AM1, C2 times AM2, all the way to Cn times AMN, added together. All right, so let's talk a little bit about notation. We notate the A as matrix brackets around the T, and then B prime comma B. So the B prime is your codomain basis, and B is your domain basis. So it looks kind of backward, I think. But we've all already seen that the dimensions of the matrix that we have are kind of backwards as far as dimension of domain space and dimension of codomain space. We saw that for Rn and Rm. We actually see that here. We didn't mention it, but notice that we started with n vectors in B and m vectors in W, or in B prime, I should say. It was n in the first space and m in the second space, but the matrix we're using is m by n. It basically flips the dimensions there. All right, so we get this notation for the image. So this was our matrix, or sorry, this is the coordinates of the output with respect to B prime. This is the matrix A that we formed. We just give it a new name. And this is the coordinates of the input relative to B. All right, that's lots of words. Let's see if we can do an example and see what's going on, because that's the important part, being able to understand how to do these problems. But just one more thing to mention. The important part of this idea is that any linear transformations between finite dimensional vector spaces can be computed through matrix multiplication. That's pretty cool. So let's see what that means. All right, so let's start with the derivative linear transformation and going from third degree polynomials to second degree polynomials. And let's let B and B prime be our standard bases for those two particular vector spaces. All right, so the process says first apply the transformation to each of the basis vectors in B and compute the coordinates relative to B prime. All right, well, the derivative of 1 is 0, and certainly the coordinates of 0 relative to B prime are 0, 0, 0. Image of x, the derivative of x is 1. And to get 1 from B prime, we need 1, 1, no x's and no x squareds. So the coordinate vector is 1, 0, 0. Image of x squared, derivative is 2x. To get 2x, we need no constant, 2 x's and no x squared. And then finally, image of x cubed, derivative is 3x squared, so we get 0, 0, 3 for our image, or our coordinate vector. That gives our matrix for the transformation, the T sub B prime B. Write them as columns. 0 is down the first column, 1, 0, 0 second column, 0, 2, 0 third column, 0, 0, 3 fourth column. All right, so let's say I want to use this matrix to help me find the derivative of this polynomial. Obviously from calculus you already know how to do this, but I want to illustrate how we can do this with matrix multiplication. All right, so first we find the coordinate vector of the input. The coordinate vector of the input is 7, -3, 5, -4. This is relative to the input basis. So going back up to B, not B prime. Everything up until this point, we've been computing coordinates with respect to B prime. This is coordinates with respect to B. The rule we developed before was take the matrix and multiply by the coordinate vector. So I take this matrix that we just found and multiply by the coordinate vector. And if you do that matrix multiplication, you get -3, 10, -12. And lo and behold, that tells me that the coordinates of the output are -3, 10, -12. So I use that for my basis. -3 times 1, 10 times x, -12 times x squared. This gives me the derivative of f prime, the derivative of f prime here. And you can take the derivative and see that we get the same answer. So this gives you maybe just a tiny little bit of insight into how computer algebra systems work. If you've seen computer algebra systems that do some symbolic computations, like do a symbolic derivative, this is how they do these kind of things. They know these rules, and they have some matrix multiplication things, some linear algebra type of tools to be able to do those types of derivatives. They have those rules built in for you, which is why they can do this for arbitrary polynomials. All right, let's do another one. Let's say we go from 2x3 matrices to 3x2 matrices by doing the transpose. That's a linear transformation. And let's let the b and the b prime be the standard bases for those two particular vector spaces. And when I say the standard ones, I mean that we'll start with a 1 in the upper left-hand corner, zeros everywhere else, and then we'll move that 1 across the row, across the columns before we drop down a row. So to show you what I mean, the first standard basis vector we're talking about here will be 1, 0, 0, 0, 0, 0. Okay, so its transposes this, and that is 1 in the upper left-hand corner, zeros everywhere else. So that's 1 times the first one, and then zeros for the rest of them. This is what I mean by going across, right? Across the columns and then down the rows. So my second one will be 0, 1, 0, 0, 0, 1. When I do the transpose, I get this one. Now again, if I go across the columns before I drop to the rows, this is 1, 2, 3, the third basis vector in b prime. So that's why I have 0, 0, 1, 0, 0, 0. Likewise here, when I do the transpose of this particular vector, I get 0, 0, 0, 0, 1, 0. That's in the fifth spot. So that's why that coordinate vector has a 1 in the fifth spot. I'll just click through the next ones, and you can verify for yourself that those really should be the coordinate vectors of those inputs, or the outputs, I mean. All right, so now taking those coordinate vectors and making them into a matrix by putting them in as columns, we get that matrix. Okay, looks close to the identity matrix, just some things flipped around. It's certainly not a transpose. Well, it could be a transpose of something, but it certainly isn't the identity matrix, and it's not the transpose of anything that we have right now. All right, so now let's see how we can use this. Okay, so let's say this is an input, and again, I said we read across the rows and across the columns, and then go down a row to the next one. So the coordinates of this particular matrix would be A, B, C, D, E, F. Now let's do the matrix multiplication. So this is the matrix we just found. These are the coordinate vectors, the coordinate vector we just found. If we multiply, notice that we get A in the first one, then the next one, when I do the second row times this column, I get the D. And then I take this third row times the column, I get the B. So I get A, D, B, E, C, F. It's like it shuffles them almost. All right, so now let's see if we can compute the transpose using matrix multiplication. Okay, so M transpose is the image of M. This is the coordinates of the image of M. So I take each of those coordinates and multiply by the standard basis. So A times 1, 0, 0, 0, 0, 0, and so on down the line. And when you add those together, you really do get the transpose of M. So what did we just show with these two examples? The first example, we showed that we could do derivatives of polynomials using matrix multiplication. Here we show that we can take transposes of matrices using matrix multiplication, which is kind of a cool idea. So we will definitely do more examples of these in class, but I wanted to give you a couple of, basically I wanted to give you the introduction of how you even form these things. Both of these examples use the standard bases for their respective spaces. So we'll talk a little bit as well and get a couple of examples where you don't have the standard basis to start with, but you can still do the same kind of idea. So, all right, we'll talk about that in class.